And after this class, next week we'll have 2 virtual classes, and that's it. Then I'm back in Puerto Rico, and we will be meeting in the classroom. The next test will be on the 26th. Let me verify. 26th of April, so we still have time. And then the final exam. I think I'm going to move the final exam to the last day because they added a day to the calendar. So I think I'm going to move the final exam to the 8th. But I will confirm with you and edit the platform so you can see that. Because right now it's on the 7th, but we had an extra day added. So that way we can use the 7 for review, and then the exam will be on the 8th. But I'll make the change later. Okay, so we left off, I introduced the idea of computing returns per period and this understanding of a general formula for computing returns for stock, let's be specific, with dividend earning stock for ex post data. It's all of these criteria. It has to be historical data, dividend paying, otherwise this is 0 per period returns. And I showed this example, reminding you that's what we're calculating, one of these at a time. I mentioned that our goal in this unit is to come up with an estimate of the required rate of return for the firm issuing stock. And the first method to doing that I introduced was known as the dividend growth model approach. And that is using market information with certain assumptions that are the same assumptions as those in the assumptions for growing perpetuity. If cash flows are infinite, but yet related by a constant rate of growth, you can estimate like this. And I showed that this is essentially a special case of the more general returns formula. Then I had you using the formula that I introduced, we calculate the return for one period and divided it up into dividend yield and capital gains yield. Someone has their microphone on. All right. This is where we ended, right? I believe we did that, and then we stopped and I asked you to work on question 9 of review 1. Did anyone have questions about it or have trouble with it? So question 1 from review 9. Sorry, question 9 from review 1. I do that sometimes. Sorry. Is a matter of computing these statistics. Now, what kind of data have I given you here? Which set of statistics are you going to use?
The probability ones?
Right, and they're called, what did I call them? Ex ante, right? Ex ante data. The ones with probabilities in them, I refer to as ex ante data. So you're going to use the formula from this document, these formulas here, down here, because the data has the P's in it, okay? So that's what you're calculating. And further, you're not just going to get the returns and the standard deviation and the covariance between the S&P 500 and certain stock, I added a second stock. Did anybody try this exercise? No one? Anybody want to brag? Okay, you can brag on Tuesday because I want you to finish the entire review 1 by Tuesday. All right? The solutions are there, but you should work on them independently. Okay, so I think we left off here. So the first method I mentioned was the dividend growth model, which based a certain set of assumptions on historical data to project or predict future outcomes with a rate of return that would be constant. That's basically what you found out from this model. But what if we use statistics in a different way to interpret returns? One way would be to summarize returns over a period of time. So taking your historical data, either S&P 500 or BCE returns over a period of time, computing what would be the return of $1 invested in period 1 at the end of period 5 if you left it there. That's what the holding period return gives you. To calculate the holding period return, you multiply factors, just like rates are compounded, you're going to compound different rates to get the overall rate of return. And then you minus 1 because we want the return per dollar invested. So we need to take that dollar off to see the percentage return. So we're going to calculate the holding period return for a certain set of data, not this one, but I'm going to give you another one. Second, we're going to calculate an average return. We're going to do that as a geometric average, and then we're going to do it as an arithmetic average. A geometric average return is computed from the holding period return by converting it into an average per year. And it's done similar, if you remember how we calculated in interest rate conversions for a fraction of a year, we would in the powers impose the fraction that we would want of the year to find out over that period. Well, we're going to do the same thing here. And the fraction of the year that we want is 1 over 2t. Not the fraction of the year, but the fraction of time to get 1 period over t periods. So this looks like interest rate conversions, except the R's are changing. They're possibly different, just like here. So we're going to calculate a geometric average return. And we can also calculate just a regular average, arithmetic average return. Now, what's the difference between these? If they're not different, it doesn't matter. But if they are different, you use GAR. GAR is a better representation of the annual or periodic return over a period of time. That's because in our case, we're working with rates. How many of you have ever seen GAR before working with finance? Have you heard of GAR before? Anyone? Did you learn it in statistics? Do you remember?
I don't remember.
You don't remember? Anyone think that they never learned it before? So this is very specific to rates, right? Because for rates or growth rates or interest rates, remember we want to incorporate the compounding effect of rates, and that's what it does by using these accumulation factors. So this is more indicative of the return per period than if you added and divided them. In fact, the average return, remember what the average arithmetic average is, it's the center of gravity. And as the center of gravity, it will be pulled away towards extreme values and distort the notion of expected value just for a few values. So we really want, when we have a representative average, we want it to represent the majority of the data. And it's not necessarily a good thing to use arithmetic average return when data are not symmetric or has extreme values. So if you watched my statistics review, I discussed that. Or skew the distribution. So do not use the arithmetic return when there are extreme values that skew the distribution. And essentially for our purposes, if you calculate both of them, which is common, and they're different, use GAR. If they're not different, it doesn't really matter. Okay. All right, so let me give you the data set I want us to compute these statistics for. We're going to use this data set. This is the data set. These are actual estimates or computation or statistics calculated for the S&P 500 during the global market financial crisis of 2008. And here you see the crash or the shock in 2008, where we started at about 5%, 5.5% in 2007. And I've mentioned before the average return, and we'll see it in this portion of notes, the average return to the market returns, or the average return of market returns, is about 11% over 80-year period. So this is kind of low. It's half of that. But then this is a real crash here in 2008. Did it recover is my question. It goes up, it corrects to 26%, and then it settles at 15. It's a little bit above historic average. So the question is, determine if the market recovered by 2010. In other words, calculate the holding period return to check if we get about 11% or somewhere, at least not zero. So calculate the holding period return for this data. I have the formula here to remind you. You guys are supposed to be on the camera so that you're focusing. It's very distracting in front of your computers or your phone or your iPad. Get on the camera for your sake. So I'm going to calculate it using the calculator. You can watch me. You can work on your own, but let me know if you want me to go slower. So what I have to do is multiply the accumulation factors 1.0549. I'm going to store that in 1. And then 1 minus 0.37, because it's 1 plus, but it's 1 plus negative 0.37. So I'm going to just minus and store in 2. And then 1.2646, I'm going to store in 3. And 1.1506, I'm going to store it in 4. So my results are 1.0549, M2 is 0.63, memory 3 is 1.2646, and memory 4 is 1.1506. So I've just added 1 to these percentages. Now I'm going to multiply them. Recall 1 times recall 2 times recall 3 times recall 4. And you get that. Am I done? What do I do next? I have to subtract 1, right? That's the formula. I have to remove that principal amount because we're calculating for every dollar. And that's my result. So what is the conclusion? So my original question was, did the market recover? And what's the answer? What's the answer? You guys need to come on the camera. I'm going to assume you're not paying attention. Alejandra, very good, says the market didn't recover, right? Because for every dollar invested, investors over that period who left that dollar there lost 3.3 cents. Notice that this is rounded in the answers, and there's a decimal answer on the screen, on the calculator screen. But I'm going to continue with this rounded amount, because now I'm going to compute the average return over the period. The average return is a fraction in the exponents to partition it into parts. 1/4, and then minus off the 1, and I get this result. Let's do that on the calculator. So I'm going to add 1, and I'm going to raise to the power of 4, but invert 4, and that's not right. Oh yeah, because I have to I rounded it. Okay, let me use the rounded figure. So 1 minus 0.033 equals, then raised to the power of 4 inverted. What? 1 minus 0.033 equals raised to the power of 4 inverted equals, and then minus 1. And I get that answer. Don't forget the minus ones. So what does this give me? Who's going to interpret it for me? What does this say? Ricardo, what does it mean? Carlos, what does it mean? How do I interpret this result? Nobody? Alejandra suggests it's the average return per year. That's right. It's the average return per year. It was 4 years. We got an average of the 4. So this is the average return per year. And it is negative. So it's showing that there's a negative return per year. But this is calculated as a geometric average return. Again, for rates, that's what you use. Because they have that compounding effect that we want to capture. An alternative to calculating the average using the geometric average is to calculate the arithmetic average. We can get that from our calculator using stat mode of our calculator. So let's do that. Let's put those values. Put these values into stat mode of the calculator. How do we do that? Let's remember, this is just one variable. We can enter it into stat mode. So second data, there's something there, so I need to clear. So I'm clearing out my worksheet and beginning to enter figures 0.0549, enter down, and I skip over y because I only have one variable, I don't have two. Then 0.37 negative, enter, scroll down, then 0.2646, enter, scroll past the y, and finally 0.1506, enter down. So I have all my data here. And compute second stat. There are 4 observations. Here's the mean. That's the weight. That's not the geometric average. It's just a regular average, arithmetic average. So that's the mean there. Okay, so that's the geometric average return. The arithmetic average return looks like there was 2.5% return per year. Which is a better measure of return? Because of the effect of compounding, we go with this one, the GAR. If they're different, choose GAR. This is actually misleading. So GAR is the answer, not the arithmetic average. All right. Any questions? Are you having any difficulties computing those values?
No.
No? Alondra? Was it you?
Yeah, no, I don't have difficulties.
Okay. All right. So looking back at the data set, talking about a rate of negative 3.3% tells us something, but it doesn't tell the whole story. It doesn't capture this crash or the shock of negative 37%. It doesn't capture the recovery of 26%. We want to measure a statistics measure of the volatility. How do we measure volatility? So here's a graph showing you the returns historically. So over an 80-year period, the returns to 3 asset classes, S&P 500 as a measure of risky assets. It's a proxy for a diversified portfolio or how the market performs, we have 3-month treasury bills and 10-year treasury bonds. The darker dash one is the one you see here that's always positive. So what do we see? Some things that we see here are the extremities, the extreme dips and the peaks of the S&P 500 over the years. This is the beginning of the Great Depression, right? Well, I guess it began over here. And this is the 2008 crash. This was the oil crisis in the 70s. So you see it all here. And investors in the market, I think they're aware of these shocks, but they're hopeful of getting these peaks, right? There's nothing in compares to the high returns of the stock market over time. And like I mentioned, on average, and we'll look at that, it has a positive annual return of around 11%. So risky assets are more volatile. And then you see the less volatile is the 3-month treasury bill. It's much more flat. It's above zero, whereas the treasury bonds do dip below zero returns, and they do go up, and there's much more volatility. Both bonds are guaranteed. They have a guaranteed return, but they're subject to other factors in terms of their, their uncertainty in return. So this is tracking the market valuation. Remember, for bonds, the price and the variables that determine the price of a bond are dependent on the yield to maturity. That's what this is capturing, the yield to maturity that is affected by sale of bonds in secondary markets. So anyway, without getting too much into it, what you see is the most volatile asset class are stocks, okay, compared to bonds. So what measures volatility? What statistic will capture that? Not the mean. What is the statistic that captures volatility? Diego. Alondra says standard deviation. That's right. So it's going to be the standard deviation that does that for us. We calculate the variance. Notice it's the variance formula that we're familiar with. This is the average of squared deviations from the mean. Remember, I started this unit talking about this working with ex post data, but later I'm going to work with ex ante. Always be clear what kind of data you're working with so you're using the right statistics. I gave you a time series of data where every data point was equally significant. And so I'm using the sample standard deviation formula. I take the variance, sample variance, and I get the square root to get the sample standard deviation that I write like that or like that. So now I want you to go back to your calculators and pull out that number, because if you left the data in the calculator, you could continue with the arrow to find the standard deviation. So what is the sample standard deviation of the data of the S&P 500 returns over that volatile period? What does the calculator say?
2769.
You think that's high? Is that a large variance? So yeah, it depends, right? Everything is relative. You can calculate it manually or use your calculator. You should be able to do both. So the standard deviation is the square root of the variance, which is 27.7% or 27.69, like we were just told. And it is rather high. It is rather high. How do we interpret a mean and a standard deviation? So, we got a mean of an arithmetic mean, let's be clear. So we got an arithmetic mean of 2.5%. What do we do with these numbers? How do we look at these? How do we interpret? What does it mean to us? And notice I'm not talking about the GAR right now. I'm just going to talk about the arithmetic mean and the sample standard deviation. Sample mean and sample standard deviation. What do I do with these numbers? Right. Nobody knows? Okay, so what do I do with these? Well, if I assume the data are approximately, or say approximately normally distributed, what can I say? Well, first of all, how can I do that? I would have to then have seen symmetric data, at least symmetry in the data, and I should see a dispersion of the distribution such that what? Most of the data will be around a center, which we end up calling mu. Yeah, so if you have a lot of data, whatever you find for the mean, you just call the mu. The population mean, because we're saying the sample is representative and we have enough of a pattern to make this assumption. And most of the data, is centered around the mean. How much of the data is within one standard deviation of the mean? So what we do is we make this our mu and we make this like our standard deviation. We use them as estimates, but then we can say it's approximately normal. How much? Told you guys had to be experts in statistics by today. So how much of the data is within one standard deviation? Sophia. Yeah, the L. Guys, I know you're not there. Elizabeth. Come on. Show up. Denzel.
I'm not really sure, but Alondras has said in the chat 68%.
Denzel, you're not sure?
I'm not certain right now.
68% of the data is in one standard deviation from the mean. How much was within two? If you have problems with statistics, anyone, I put the reviews of statistics on the platform for you. So you learn the basics for this class, because this is not a statistics class, but it's assumed you know statistics. These fundamentals. Oops. So within 2 standard deviations are 95% of the data. So let's first begin. Tell me how much, give me an interval of values. What does that mean? That within 1 standard deviation are 68%. So we're going to take 2.5. We're going to add and subtract 27.7% to it. Give me the upper and the lower bounds. Yeah, so Joash, thank you. 5.2. So he's got 25.2% as a lower bound and a comma, 30.2%. So it means that but isn't that a negative, Josh? It's a negative. You subtracted it, but you didn't put the negative. So within 1 standard deviation, we're deep in the negatives at negative 25% return. Okay, so there's a 68% chance of the observations being between negative 25% and 30%. That's pretty bad, right? Negative 25%. So 68% of the observations, or in other words, 60%, 80. So since we assume this is representative of the population, we say 68% chance that the observations will be between negative 25 and positive 30. And then you can keep going and calculating within 2 standard deviation. Within 2 standard deviations, you find how much, Denzel?
Was it 95%?
Yeah, see, you remembered. I knew you would remember. 95%. You guys have a lot you've learned in your mind. You just have to sort it out. What is, okay? What is what? So between there, under the curve, are 95% of the observations. And within 3 standard deviations, what about 3 standard deviations?
Is it a 97.5?
97.9. Very close. Thank you. Anubis, right? 97.9. So even though I have a very sketchy drawing here, very messy drawing to call it. You get the idea. You've seen this before.
Sorry, Professor, it's 99.7.
Exactly, 99.7. 99.7. So between there, you have 99.7%. 99.7% within 3. So what does it mean? It means that most of the data are within 3 standard deviations, and that is not necessarily the case. And I explain all this and give you examples in the review of statistics, which you should watch. If there's 99.7% within 3 standard deviations, and we define outliers as values of symmetric distributions that are beyond 3 standard deviation, it means what percentage are outliers or extreme values. In a normal distribution. The normal distribution allows for 0.3% of observations to be outliers. In other words, there's a 0.3% chance for a unusual result. Extreme positive or extreme negative result. So having said all of this, I didn't calculate all of them. You're going to do that in a second for a different data set. The fact is that even though we did this with the data from this time period, in fact, it wouldn't be good to use this data set because I already told you not to use the, oops, I went out. I already told you not to use the arithmetic average, right? I just did it because I made some calculations here, and that's how we interpret the normal distribution. In fact, it's not for a single asset that we should assume normal, or a single stock that we should assume normal distribution, but we do assume a normal distribution in finance for the S&P 500 or market returns in general. So if you look here, historically, this is the last page of the notes. This is a histogram of the data that you saw on the chart, tracking returns in a time series. But this is in a histogram. So in a histogram, we create this distribution, and you see it's not perfectly symmetric, but it is approximately symmetric and approximately normal. And so because of that, we calculate the mean and the standard deviation. And there's the 11% I was telling you about. You see this is 0 here. So the peak where the mean is at around 11% here. And the rest of the data is distributed in a approximately normal fashion around it. The standard deviation of this data is still kind of high, but not as high or volatile as we saw for that time period of the 4 years around the crash in 2008. Notice government bonds are also somewhat, well, they're symmetric. I don't know that they're normally distributed, but you could see that they're symmetric. And because of that, you can do the same sort of interpretation. Most of the data is in 1 standard deviation. And you can check how close to normal it is by checking the percentage of observations in 2 and 3 standard deviations. And you can tell if it's normal or not, or you can make the assumption. And then why do we care about making an assumption of normal? Of a normal distribution is so we can make predictions, which we're going to do in a minute. Here are treasury bills. Treasury bills, oh, I just want to point out, here's the 0. So it looks like the mean is, slightly above 0 for government bonds. And here's the average, 5.2. Significantly lower, it's half of stock returns, but accompanied by less volatility. And it looks like, and something we're going to talk about later, is this relationship between risk, arithmetic mean, risk, the standard deviation, and return, the arithmetic mean. Okay, again, we're doing this for symmetric data. Treasury bills here are positive, whereas government bonds can be negative. They have like a negative return. But here, no, they're always positive and skewed as a result. They are They have a mean of 3.5, the lowest, and accompanied by a very low measure of risk or volatility, 3.1%. So going back to this one, the stock, we're going to use the mean and the standard deviation, and I'm going to ask you to answer these questions. What is the chance of positive returns? And what is the chance that returns will be less than negative 30%? Using this data, so I've taken the results of the mean and standard deviation from the historical data, called this the mean, mu, and called this sigma, treating it like a population. And now I want you in the space provided, I will display this distribution as a normal distribution and then answer these questions. So in the middle, I'm going to mark I'm going to mark 11.4% as my mean. And I'm going to add and subtract 11.4 plus 19.7. And what do you get? What about minus sigma?
Okay, so it gives you on the positive one 31.1, and it gives you on the negative one negative 8.4.
Thank you, Alondra. Negative 8.4.
No, sorry, it's 8.3. Sorry.
Yeah. Negative 8.3%. So we're going to mark them. This is 31.1. And this is negative 8.3. And then keep going. Now do 2 standard deviations. which is 11.4 plus 2 times 19.7. $11.4 minus 2 times 19.7. So fill the whole chart and then we'll interpret. So for people who took class with me before, this is very repetitive, but I'm going to be adding more material. So just stay tuned. Oh, it's really high, right? It's going to be 50.8.
It's 50.8, and let me do the other one. Wait. It's negative 28.
Very good. Okay, and we got one more to do. So one more set, and then we will make our we'll answer the questions.
Okay, so this third standard deviation is going to be 70.5,
Mm-hmm.
and let me do the other one. It gives you negative 47.7.
Okay, so I think we have our answers. Mostly, we didn't have to go as high, but let's just finish this off. Thank you so much. But we have our answers, right? The questions were, now back to the questions. Because we can assume normal distribution for S&P 500 returns, we can make some predictions or we can alleviate uncertainty for questions like this. What is the chance of positive returns approximately? Where are the positive returns starting? Somewhere between here, right? Now, I don't know exactly where, but you guys could use a normal distribution to find it. But if I was, if I had to guess, it's at least bigger than, how much is this over here? What's the probability of being?
50%.
Right, so it's at least 50%. So the chance of positive returns are between, how much would it be if it was here?
Then 68.
No, 68 is if it's in the middle, but you're close.
Oh, yeah.
So this is 32. This is 50. Right? That's 32 because, not 32, it's 68, 34. Oops. This is not 32, it's 34. How did I get 34? I just took 68 and divided it in half. This is 34. This is 50 over here. So it's between, it's somewhere in here is the 0. I don't know exactly where because there's a curve here. It's hard. I can't just divide it in half and stick it there. I have to observe the curve. So it's between 50 and 84% is one answer. The other thing you can do is get a normal distribution or use Excel and you can get the exact answer. But for my class, you know, you just got to make approximations. So the best answer, just using this curve, is between 50% and what did I say, 84%? Or you could use the normal distribution, standard normal. You can say X, well, the probability X is greater than 0. And then standardize with these and get the standard normal and figure it out. Basically, that's what you need to do. That looks really messy. Let me do that again. But I'm not expecting you to do that in this course, but you should be able to. Got it? Okay, what is the chance that returns will be less than negative 30? That one's a little easier. So where's negative 30? It's about here, right? It's a little bit below that. So what does that correspond to? How much is that way? What percentage of observations are there? Going back here, 2 standard deviations was 95 in the middle, but how much outside? 95 in the middle, but 2.5% on each side. I'm hoping this is ringing a bell for you. I'm going kind of fast. Just close to 2.5% will be lower than that because this is on the, this is at 2 standard deviations below. Okay, so what is the chance that returns will be less than negative 30? Close to 2%, 2.5% chance. So in the review 1 that I've given you, you're going to practice this. There's problems like this that you can practice. Questions? If you want to use Excel to get the answer, the exact answer for this, see if I can do that. Let me see, Excel. Password. Why I never like to open Excel. I should just use it on my computer. Okay, if this doesn't work, I'm just going to open my computer. All right. I need to clear screen here. Do another one. So if you wanted to do that in Excel, you hit normal distribution, and you put in, so this is going to give you the percentile, the area to the left. So you put in 0 here, you put in the mean of 11. What is the mean? It was 11.4 and standard deviation 19.7. $11.4, 19.7, and then you can say 1, it's cumulative, and that will give you the left side, and then you have to take 1 minus. So there you have it, 72%. If you guys want that code, and you don't, for my class, you don't need to do this, but for, I guess, for future reference or other classes, it would be nice to have that. Oh, it's not letting me. Oh, no. No, I made a mistake. I'm trying to keep the text on. Okay, so that's the answer there. Okay, so it was between, we said, I copy this. Put this here. Anyway, it should go here. So yeah, we got 5284. So the answer was like 72%. You could do it with a table too to get it exact. All right, so that is that. One last thing to talk about before you go. We have a few minutes. We recognize that in general, the higher return corresponds to a higher standard deviation. This is the highest small company stocks over this time period. Highest return, but also the highest standard deviation. So it's capturing the volatility, uncertainty, or risk associated with holding that asset class. Here are the distributions for them. So what we like to say is the lowest asset class is treasury bills, right? So these are UST bills at 3.8% on average over this time period, with a standard deviation of 3.1, just beating inflation. You see, the inflation is 3.1. So as in order to have a store of value, in order to keep up your savings, maintain your savings at a rate that's higher than the rising cost of things or inflation, T-bills is a must, right? So T-bills should be held by investors, and then with a low risk as measured by the standard deviation, but other asset classes exist, and that's because of the higher return. So to take on this added risk over and above what you risk with T-bills, the volatility of T-bills doesn't, even one standard deviation doesn't put you in the negatives, right? If you do plus and minus 3.1, but it does for the other asset classes. It's going to throw you into the possibility of a negative, and you'll do that. You'll do that because of the higher return. So what we talk about in finance is called a risk premium. This captures the idea that we are prepared to pay, we are prepared to take on the added risk over and above T-bills because of the higher return. So we can compute T-bills relative, risk premium relative to T-bills. We use the notation RF for T-bills as the risk-free rate. We take the risk-free rate and compare everything to it. So the other ones would be returns or arithmetic returns, which we can calculate and interpret for these types of assets, all right? So we'll assume that they are symmetric and approximately normally distributed in each asset class. So a portfolio of assets in that class, the mean is a good representative of expected value, and you're going to subtract off the risk-free rate to compute the risk premium for each asset class. So I'm going to ask you to do that. And you can also do that for these. Actually, I did it. So I computed here the risk premium to incentivize investors to invest in the stock market. They have a risk premium of 7.9%. How did I calculate that? I called T-bills risk-free. I call these our market. I put a bar here, and I calculate our market minus RF to get 7.9%. And I can do the same thing for the bonds, and I can do the same thing for all of these. So for next class, I want you to compute all the risk premiums, and I want you to complete review number 1. All right, so that's what you're going to work on this weekend. And we're going to continue next class with the next set of notes that are found here. Risk and return, CAPM for capital asset pricing model. So I want you to catch up and be with me here for next class. Okay. Any questions? Also, you have to do, well, this is part of review 1. I want you to do all of this. At least attempt it. And I will fix the answer key to add in those answers that are missing from the solutions. Not answers, but the solutions that was for here. And I don't know how I missed that in this one. I have them. I just have to paste them in. Any questions for me? I'll check the chat. So next week we're going to be online, and then I will be back in Puerto Rico on the 12th. Just keep in touch. You guys can text me if you need anything. I can meet with you virtually if you need anything. I will post this video into YouTube. And if you have any issues with me posting it in YouTube, let me know. I can make it private. It's just easier to find if it's public. I mean, not that anybody's looking for it. It's just, if you're looking for it, it's easier to find. if it's public. Okay. I'll let you go. Have a good afternoon. Have a good weekend.
Thank you, you too.
Take care. Bye.
So, Professor, bye.
Thank you, Denzel.
Thank you, Professor.
Thank you for coming on the camera, Denzel, and answering my questions. Ciao.